This is the machinery behind ChatGPT, Gemini, Claude, all of them. And it's far simpler than it looks. Each word doesn't just get one context infused into it. The model creates multiple infused versions of the same word, one for every attention head. Each head focuses on a different angle of the sentence: grammar, meaning, long-range links, local patterns, all at once. Then somehow, the multiple rich contexts that the heads created fuse into one. A single, dense representation that packs together all those perspectives, compresses every viewpoint, and turns scattered insights into one unified meaning the model can actually use. Then they are all fed into a normal neural network. Okay, so picture the sentence, "The cat sat on the mat." To us, that's plain English. But to a transformer, those are vectors, giant lists of numbers that represent meaning. Every word already has its own learned personality, but two big pieces are still missing: where the word is in the sentence and what words are around it. Because, yeah, the cat sat on the mat is very different from on the cat sat the mat. And the word bank changes a lot depending on whether it's near river or robbery. So the model fixes this by updating every word vector with two things. Number one, position or location. Transformers add positional info using sine and cosine waves. Simple math that gives each word a unique pattern depending on where it appears. And number two, context. Now this part is the good stuff. We use the attention mechanism that everyone talks about, but almost no one knows how it actually works. After this, you will. Attention lets every word look at all the other words and figure out which ones matter most. It works by adjusting the value of a word, like cat, using contributions from every other word. Each contribution is weighted by how closely that word relates to cat. For example, the model checks how related cat is to sat and adds a fraction of sat's value. It then does the same with mat and every other word in the sentence. Each word adds something, and the amount it adds depends on how strongly it connects to cat. Remember, attention does this in every dimension separately. The only thing left is defining what that similarity score actually is. And honestly, it's kind of trivial. We use dot products. I know that sounds fancy, but it's really not. To measure how similar two words are, we multiply their values dimension by dimension. Take apple and settings as an example. Multiply apple's dimension 1 by settings dimension 1, multiply apple's dimension 2 by settings dimension 2, and so on across all dimensions. Where both words have high values in the same dimension, the product comes out high. If one of them is low, the product collapses to almost nothing. Maybe dimension 7 happens to encode something like technologiness. If both words score high there, you get a strong contribution to their similarity. And if they never overlap, if one word has 0 where the other has a big value, the product is 0. 0 means 0 overlap. 0 overlap means 0 similarity. That's the whole idea. Matching highs reinforce each other, mismatches vanish instantly. Crazy simple. So basically, dot products. High score, those words relate. Low score, they don't. Then using those scores, each word mixes in information from all the others. So every word you see ends up carrying who it connects to, who it depends on, and what's happening in the whole sentence. Now multiply that process. Transformers don't use just one attention mechanism, they use tons. These are the attention heads. Each head picks up on different patterns: grammar, long-distance relationships, topic, style, whatever the model learned from billions of sentences. So take a word like cat. Instead of getting one updated vector, it gets 5 different versions, one from each head. Then, the model stitches them together into one big, super informative embedding. Now that the word knows its position, its context, and a handful of different perspectives, the transformer feeds that into normal neural network layers. Nothing magical, just standard feed-forward stuff with backprop doing the updates. If you take one thing away from this video, let it be this. A multi-head transformer takes a word, creates several context-aware versions of it, merges them into one rich representation, and sends it forward. That's why transformers understand language so well, and why they run basically every modern AI model today. Thanks for watching. If you're interested in seeing more of this content, then don't forget to subscribe and drop any questions or comments down below.